emitted alpha particles. And they let these bounce off the gold foil, and they had a detector, which was this screen. When the alpha particle would hit it, you could count the number of hits. And what was really interesting about this is that it told them something about what was going on inside the atom. At the time, there was the view that the atom had charge kind of distributed around the atom in this model, which I think sometimes people call the plum pudding model. And if this was correct, what you would expect to see is these particles going through. And for the most part, they just kind of have small deflection angles, and you would observe lots of counts on one part of the screen. But what they figured out, what Rutherford and colleagues figured out, is that actually rarely you would see a count from an alpha particle that bounced back with a large deflection angle. And this tells you that there's actually a nucleus at the center of the atom. So with that information, you can then change your picture a little bit about what's going on inside the atom. You have electrons on the outside with the nucleus at the center. And then by other experiments, it was figured out that this nucleus actually, doing the same kind of scattering experiment, the nucleus actually has other particles inside of it, things like, so there are quarks inside the atom, inside the nucleus, being held together by gluons. And I'll talk about this in a little bit more detail. So the picture here is that we're trying to go to smaller and smaller scales. Our tool, or our microscope, is an accelerator. And the reason for that is that we want to go to smaller scale. And you can think of this from the de Broglie relationship, where to go to smaller scale, you need to go to higher momentum. And so elementary particle physics is high energy physics. So if you think of it in terms of the different distance scales that we know in the universe, where we're sort of sitting here at the middle, microscopic things like cells and viruses are say, a few microns, but we want to probe nuclei and then things at even smaller distance scales, which we have to do by going to very high energies using accelerators. There's been an evolution of accelerator energies as a function of time, and this just shows a few points from proton beam experiments as a function of time. And you can see that in the early 1900s, we had things like cyclotrons, where you have an electric field and a magnetic field to accelerate a charged particle. And then over time, this was increased by roughly an order of magnitude every 2 decades or so. There's a few points you might recognize, especially at the top. You might recognize 2000 GeV, or 2000 times the mass of the proton, roughly. That's the most recent US experiment at Fermilab. And then the highest energy one is the Large Hadron Collider. And I'll be discussing that in some detail later in the talk. So what I'm going to do in this talk is I'm going to describe a little bit about the Standard Model, in particular the questions about in particular the discovery of the Higgs boson, and then some open questions about the Standard Model. I'll talk in some length about the actual experimental details, the Large Hadron Collider, the ATLAS experiment. Then I'll talk about one particular search, which is a search for invisible particles, and then talk about what this kind of discovery would mean. So the Standard Model is the summary or the theory that describes all of the interactions and particles that have been discovered at this point. You've probably seen this table before. The kinds of particles that make up the atom and the nucleus are the quarks and the electron, which are just shown in this first column. Of course, there are mediators of these interactions, the gluon for the strong force, the photon for the electromagnetic interaction, and the W and Z bosons, which are responsible, for example, for radioactive decay. But there are other particles in the Standard Model as well. There are heavier copies or generations. For example, the top quark is the heaviest particle in the Standard Model. There are also heavier versions of leptons, such as electrons, muons, and taus. And then there are neutrinos. The neutrinos only interact electroweakly, and so they are only interact with the W and Z boson. Now, the Higgs boson is the newest discovery of the Standard Model, and it's relatively new, and it plays a unique role in pulling all of this together, in the sense that it gives mass by the mechanism of electroweak symmetry breaking to all of the massive particles in the Standard Model. So the Higgs boson was discovered by the LHC, and it was discovered in 2012. What you can see on the left-hand side is the statistical proof that we had discovered a Higgs boson with some indication of the mass. Now, this plot folds together a whole bunch of information, and I'm going to explain some of the details for the kinds of concerns and issues that go into making this kind of plot. The right-hand plot shows you number of events, which is the number of kind of snapshots of our detector. And you can see in red, the background events as a function of the mass of the particle. And then the blue is the observed, is the expectation given a Higgs boson with that mass. And the black points are the data showing you that there's a particle that's not described by the other parts of the standard model, excluding the Higgs. And so there's an easy way to see that there's a new particle there. And this is updated with a little bit of more recent data after the discovery. So in 2013, this has some global significance in the form of a Nobel Prize to the theorists that came up with the mechanism of spontaneous symmetry breaking for the Higgs boson. And it was also mentioned, which is significant, that ATLAS and CMS experiments played a critical role in discovering the particle. And the two experiments are shown here. Each of them have several thousand people. I think you just see a snapshot of those people in each of these pictures. So this was a remarkable accomplishment. That said, the standard model is enormously successful, but there are a number of things it doesn't explain. So I'll go through a few of these, and there are certainly more questions about the standard model, but one of them is dark matter, and I'll talk about this in the coming slides. But there's a lot of matter in the universe from astrophysical observations that are not explained by the standard model. There's some questions, theoretical questions about the Higgs boson, particularly the mass, and I'm also interested in this problem, so I'll mention that. There's the unification of interactions, so can we put everything together into a single theory or unified theory? Supersymmetry has this kind of feature, so I'll also mention this kind of question. There are other issues that I won't really address as well, and there's a long list of fundamental theoretical and also empirical problems that we want to address. So I'm going to just mention a few of them, and not all of these problems are really particle physics problems per se, or at least we know about these issues from astrophysics. And so one of these examples is dark matter. So this is something that has been known for some time. For example, in the 1930s, and then probably more convincingly in the 1970s, it was noted that the rotational velocity curves of galaxies as a function of position in the galaxy, the distribution of velocity doesn't match what you would expect given the visible mass from stars. And so what you expect is this red line, and what you observed is the white line. And so that suggests that there's additional mass that you can't see, which is referred to as dark matter. It turns out that since then, there's a lot of other lines of evidence for dark matter. There's a lot of other lines of evidence for dark matter, one of them being gravitational lensing. This is really an interesting one because if there's a very distant galaxy and there's some dark matter in front of it, then the light from that galaxy will be lensed or bent around that mass because space-time is curved here. And so you can use this technique, or astrophysicists use this technique to infer the location of dark matter, and it leads to these kind of nice visual displays where the blue comes from the inferred mass distribution from dark matter, and then the pink is from X-ray emission from dust. And so you can see that there's, using this kind of technique, you can show where there's dark matter. And there are other lines of evidence as well, which I won't go into, which is probably more astrophysical evidence. But these are some of the reasons why we think that there's additional questions that the standard model can't answer. Numerically, it's also very significant. This chart also includes dark energy, which I won't go into, but even if you just look at the atoms and the dark matter in the universe, the dark matter substantially, it's a larger fraction than the atoms that the standard model can explain. And so this is really an exciting time in the sense that we have the opportunity to explain what this dark matter is, and try to discover it and study it at a lab. There are also questions about the Higgs boson itself. The Higgs boson is the only spin zero particle in the standard model, which means that it has some unique features. And one of those features has to do with its mass. It turns out that the Higgs boson has these quantum corrections where there's a loop, where this is a Feynman diagram, and this is a virtual correction to the mass of the Higgs boson, where in this loop there can be the heaviest particle in the standard model, which is the top quark. It turns out that this is a term that likes to be very large. So because it's such a large correction, it can lead to a sort of fine-tuning of the standard model unless there's something that will cancel it out. And so one possible way to do that is by adding another particle that is very much like the top quark but has a different spin, and so it will cancel out this correction, and it can cancel very closely to make it a not fine-tuned theory. And so one way to think of this is that this is a suggestion that these large corrections imply that there's a new particle. Now, to tie that back in with dark matter, we also know that there's some indication that the standard model can't explain everything there is. There should be other particles. And so it could be that there's additional set of particles that kind of cancel this off and that lead to dark matter. Now, the Higgs being the newest particle of the standard model, it's also interesting to focus on this. It could be, it turns out, for some kind of interesting theoretical reasons, that the Higgs boson decays into another non-standard model particle. It may or may not be related to dark matter, but that's at least one hypothesis. And the Higgs boson could be a portal, at least in a very general sense, a portal to discover the unknown. So you imagine on one side you have the standard model with the Higgs boson, and then that is a portal or a way to decay back into some other dark matter particles. And it could be related to much more kind of theoretical questions related to the fine-tuning of the Higgs mass, called the hierarchy problem. So the next section of this talk is about the ATLAS, or about the LHC, the Large Hadron Collider, and the ATLAS experiment. So I'll talk to you a little bit about the Large Hadron Collider, what happens when the collisions from the proton beams from the collider are collided at the experiments. I'll talk to you about the actual detector, the ATLAS experiment, and show you a little bit about how it works, and then how we can reconstruct or see different kinds of effects, in particular, how we can see invisible particles. So the Large Hadron Collider is the world's highest energy particle accelerator, man-made accelerator. It's a 27-kilometer circumference collider that is roughly under where this red line would be in Geneva, Switzerland. And just for scale, you can see a couple of things. You can see the airport right here. So this is a really substantial experiment. It's, of course, underground, so this red line is just indicating where it would be. The center of mass energy of the proton collisions is 13 TeV, or about 13,000 times the mass of the proton. The collider itself has some interesting features. One of the key features being the dipole magnets, which bend the beams and then allow them to stay in that in the circumference of the LHC. It has two boreholes at the middle, are different beam pipes for the protons traveling off of the directions. It's superconducting and super cooled. There's over 1,000 dipole magnets that make this feasible. You can see one of them being lowered into the LHC cavern here. And this is also a very long-term experiment, something that was conceived of in the 1980s, started in the 1990s, first data in the 2000s, taking data now, and I'll come back to this at the end, but long-term experiment, they will keep operating for a number of decades more. So the LHC accelerates the protons, brings them together, and collides them. So what happens? They collide at an interaction point. You bring them together very close together. Some protons collide, and then something interesting can come out in a fraction of the events, and then they'll produce other particles that we measure in our detector. So what we want to do in our ideal detector is we want to measure their energy, we want to measure their momentum, and then identify what kind of particle is coming out of the interaction. The way we do that is by building a really substantial detector. I work on the ATLAS detector, and so this is the detector I'll be describing today. This is a cartoon of the detector. You can see it's 140 feet long. It's 80 feet high. If a person were to stand on it, you would see it'd be rather small standing here. The detector is made up of a number of sub-detectors. So from inside out, there's the beams collide here, and then there's a tracking system, which is at the very center. This is a silicon tracking system which has pixels and also strips of tracks. This is for measuring hits, it can be converted into charged particle momenta. Then there's a calorimeter. There's two calorimeters, actually, a liquid argon calorimeter and then a tile calorimeter. These measure the total energy deposited by particles produced from the collisions. And then there are magnetic fields that bend charged particles. And then on the outside, there's a muon system for reconstructing muons. There are over 100 million electronic channels that are saved to take a snapshot of the data. And so this is a really substantial experiment with thousands of people working on it. I know, for example, the UTA group has a lot of contributions from the tile calorimeter, so working on this part of the experiment. So I want to go into a little more detail on the kind of particle interactions that occur when there's a proton collision. So there's lots of things that can come out of these interactions. You can have, for example, an electron. The electron will bend in the magnetic field, deposit energy in the calorimeter, so you can measure both of those things. The muon, it's a charged particle, so it bends. It doesn't deposit anything in the calorimeters, and then we can measure muons in the muon chambers on the outside of the detector. One thing that's really important for the kind of analyses that I'll be describing today is jets. So this is what happens when you have a quark or a gluon. These are not stable particles in the standard model, so they form hadrons, which are then reconstructible by the detector. And you can see if they're charged, you can see them as tracks, and then otherwise you measure their energy deposits in the two calorimeter systems. Another thing that is really important is what happens to the neutrinos. So the neutrinos are part of the standard model, so they don't have a significant enough interaction with the detector to actually see them. So they essentially just go right through. And that said, we can still say something about the presence of neutrinos in some of the events. And I'll show you some ways we can do that. For now, I'll also point out that because these particles don't interact with the detector, that's also how dark matter particles would look. So I want to show you some different kinds of events for what the detector sees when there are proton collisions. So this is an event display, which shows a snapshot or a single kind of readout of the detector showing the different components or subdetectors. This shows the transverse plane, and you can see there are two back-to-back things happening on different sides of the event. On the right-hand side and left-hand side, they look very similar. The blue is for the electromagnetic contributions. The yellow-orange is for hadronic contributions, and so you can see there are two back-to-back jets. These could have come from the decay of a quark or a gluon, which then shower into these observable particles. You can also see tracks at the center of the detector. There are some tracks you can sort of see are associated with each of these jets, and then there are just a lot of other tracks. And I'll explain where those come from in a minute. You can compare that to this event display here, where you can see on the left, you can again see jets, but on the right, you see an electron. Here, there's just a track, and then there's electromagnetic energy deposited by the electron. So we take these snapshots of the detector, and then we reconstruct or identify different features that we want to use to analyze the data. One thing that's really important for looking for dark matter is to find invisible particles. These don't interact with the detector, so we have to use momentum conservation. And so what we call this is missing transverse momentum, missing transverse energy, or MET. Essentially, I'll use those terms interchangeably. And what this does is it looks at the transverse plane perpendicular to the collision axis, and it looks at all of the momenta of all the different particles that we can measure and looks for an imbalance. So in this event, you can kind of see what's going on. There's a single jet on one side of the detector. This particular jet actually has a tremendous amount of energy. It's a substantial fraction of the center of mass energy, actually. And so you see there's a lot happening on one side of the event and then nothing on the other side. Because momentum is conserved, you know that this doesn't, this can't happen unless there's another particle in the event that would balance this out, but didn't deposit anything in your detector. So that could be a dark matter candidate. It could be a standard model neutrino, but you know that there's something in this event that had about 1.7 TeV of momentum. Another thing that happens that kind of complicates these event displays, and you could already sort of see it, is the fact that there are multiple interactions in every collision. So for one thing, the proton are collided as bunches, so there's lots of protons that can collide in the same snapshot. And so you end up with these kind of zoomed in images that look like this, where there's something interesting, there's two interesting muons which are shown in red, and then just a deluge of tracks shown in blue. And each of these can be traced back to a single vertex or a single proton interaction. But you can see that there's a lot going on here besides the one thing that is really interesting. And so that's something that is important at all stages of the analysis, from trying to get rid of these effects in terms of calibrating the detector, and in terms of saving the events in what we call the trigger system. So as you might have inferred by looking at these complicated pictures, the event size is actually quite large for ATLAS. It's about 1 megabyte per event. And because the LHC is so large, it can fill many bunches of protons into the LHC. And so the event rate actually works out to be about 40 megahertz, or 40 million times a second. So if you work that out, it's about 40 terabytes per second, roughly, of data that would come off the detector. So we have to deal with this in some way. We can't save that amount of data. So what we do is we take off some, what I'm calling here partial data, which is some subset of the detector information. It turns out that we take calorimeter information, this analog, and then we take some muon information, and that gets put into some custom electronics that run dedicated algorithms, and they can make a decision in 2 microseconds to decide whether or not you want to keep the event. All of these pieces of electronics are custom built for the ATLAS experiment. The board shown here is part of the system that I work on for the calorimeter trigger, and it does everything from digitized analog signals to doing some basic signal processing to running some sort of simple algorithms to do things like identify jets or calculate the momentum imbalance in the event. After that's done, we can save about 100 kilohertz, so it's a pretty significant reduction in rate, and that's small enough amount of data that we can put it into some temporary storage. And then we have a very large computing farm which can access that information and take on average a second per event to process all of that data before writing it out to permanent storage. So when I say 2-level, it means we have a hardware and then a software trigger, and we have to do all that we can to reduce the things that are not interesting before we save them to disk. So that gives a lot of introduction. I've talked about things like the theoretical problems, the things that are interesting, that give hints that there might be physics that isn't explainable by the standard model. I've talked about how we accelerate things with the LHC and the ATLAS experiment. The rest of this talk now, I'm going to shift to active research. This is largely based on 3 papers. So I'll be talking a lot about search for Higgs to invisible decays with the ATLAS detector. So this is from a paper that Andy and I worked on earlier, about a year and a half ago. And then an update for that, which has a little bit more data in it. And then a paper about the trigger system, which I also worked on recently and is important for this search. So if you see 2 different links for the same analysis for Higgs to invisible, it's because they come from 2 different searches. So that's what I'm going to talk to you about next. I'm going to talk to you about the search for Higgs to invisible particles. So I'll talk a little bit about why and how you might want to look at this. I've talked a little bit about why already in the context of dark matter, but I'm going to expand a bit on that. So if you go back to 2012, the question was, now that you had discovered the Higgs boson, was whether or not the Higgs boson conforms to the standard model, or whether it exhibits deviations due to new physics, which means not standard model. On the other hand, the hunt will be on for whatever new physics complements the Higgs boson. So this is from 2012, and I think it's quite prescient now as well, because we have a lot more data, so we can continue to press on this question. So essentially, this breaks down into 2 categories of research. One is to measure the Higgs boson and look for things that are not expected, and the other is to come up with a hypothesis, go out and look in the data for that hypothesis to see if there is some smoking gun of new physics in the data. So I'll be focusing on that second kind of proposal in terms of looking for Higgs to invisible decays. So basically what we're proposing is that there's a Higgs boson, it has some interaction to an invisible particle, which could be dark matter or related to dark matter, and it has some relatively large, it's relatively large rate. Now, the standard model also makes the same kind of invisible final state or final process, but it comes through this process where there's two Z's, a Z and an off-shell Z boson that then decay to 4 neutrinos. And the rate of this process is 0.1% of Higgs bosons, or a branching fraction of 0.1%. And so we're looking for something relatively large compared to that process. In principle, it doesn't have to be, but the much larger branching fractions are not excluded, and so those are very interesting and theoretically related to things like dark matter and theoretical ideas like supersymmetry. So one question you might have is, you did measure the Higgs boson, so how do you know that that you're still allowed, based on that measurement, to have some substantial fraction of invisible decays? And so we can answer that question. We know what the branching fraction or the rate of the Higgs boson decaying to the standard model processes are. So we know, for example, that the Higgs boson decays to two B quarks, with 57% branching fraction. So that's the biggest one. And actually, you can see that in this plot here, where this is a relatively recent discovery by Atlas showing that we can actually see this process. It also decays to a number of other processes. So each of those comes with an uncertainty. And what you do is you allow those uncertainties to kind of fluctuate down, and you can come up with a constraint on how much of the Higgs could be decaying invisibly. So based on the measurements we have, up to 26% of the Higgs bosons could be decaying invisibly. This does come with some caveats in terms of how you do this analysis. It also is a little bit more general than just invisible. It could also be that this is a standard model process that's or not standard model, but it could be a process that's not invisible. So it's a very general statement that up to about a quarter of the Higgs decays could be doing something that's not standard model at all, and it would be completely consistent with the data that we have. So what we want to do is make specific analyses for Higgs to invisible decays. I just want to give a little introduction to how we do that. So we're doing counting experiments, and what we do is we make a prediction for a given process. We say that that prediction gives us a cross-section, and then we measure the luminosity, which is how many proton collisions are worth the LHC, and then we can predict how many events we expect. Now, it's a little more complicated than that because we always apply some additional requirements to remove background and select signal, and I'll show you examples of that in a minute. So we apply some additional requirement, and that gives us some fraction of events that satisfy that requirement. So you multiply these numbers, cross-section, which comes from a theoretical calculation, luminosity, which we measure, acceptance, which we predict based on our requirements, and then that gives us some expected number of events. And I put some notation here, which might be useful based on the plots that are coming up. So then the question is how do you identify these events in the LHC collisions, and also what is actually going on? And so at the bottom, you can see the signal process. So here, this is one way to make a Higgs. It's vector boson fusion. So you have two quarks inside of two protons. Each of them radiates a vector boson and fuses to make a Higgs boson. In the final state, there's a Higgs boson and then two additional quarks. This has a cross-section of 4 picobarns, which, given the luminosity we have, corresponds to about 100,000 events. What else happens in LHC events? Well, there's a bunch of stuff. One of the things that happens is you can make a Z boson, just for example. This is one way you can make a Z boson, but it's about 3 orders of magnitude bigger in cross-section, just roughly. And by far the biggest cross-section is what we call QCD events, where two gluons scatter off of each other. And that's 5 orders of magnitude bigger. And so what we want to do is pick out the signal process that we can do a counting experiment that has a reasonable signal over background compared to these other processes. So I'll walk you through a little bit how we do that for this one analysis. You can sort of start by thinking about the vector boson fusion process. So again, you have two quarks radiate vector bosons and end up with two quarks in the final state. Here we're looking for a Higgs that decays invisibly. So this leads to something that isn't observed in the detector, and so therefore we can use this technique of looking for momentum imbalance or missing transverse momentum. And we can use these two jets. And they have some unique features, and you can see that in this event display, where there's two jets that are very well separated in what I'm calling eta, which is pseudo-rapidity related to the polar angle. So you look for these two jets that are well separated, and it turns out the reason that that's very nice is because that gives a nice way to separate the signal from background. So this plot shows the difference between the pseudo-rapidity of the two jets, and for signal it tends to be peaked at about 5, and for background it tends to peak at about 2, where this particular background is the Higgs Boson process, which is why I showed it on the previous slide. So you can see that these are well separated, and it gives a way to separate out the signal from background. Another thing you can do is you can look at the difference in the azimuthal angle in the transverse plane. So what's plotted here on this plot on the right comes from a theoretical calculation, but it's kind of what where this technique came from. You see the red line for signal, which tends to be peaked at lower values, and then the dashed lines from background from this process here, which tends to be peaked at about 2.7. And so you can see that by requiring the two jets not be back to back, it reduces a lot of the background. And again, the last thing is the invisible recoil or missing transverse momentum. This is where you use a momentum balance in the transverse plane. The x-axis here is the value of the missing transverse momentum, and then this is a histogram showing the number of expected and observed events in each of these bins. And so it turns out that there is actually a relatively sizable contribution of standard model processes, even with a lot of missing ET in the event. And the reason is you have these processes like the one shown here, where there's a Higgs boson that decays to neutrinos. Those are not seen by the detector, and so you can't get rid of them. And they show up as missing transverse momentum. The blue shows the signal, and what you would expect to see if there was a large signal deviation is an excess of events compared to the prediction from the standard model. There's also a ratio here, so you can see that, and you can see that things do kind of move around, but there's also a large uncertainty band related to how well we can calculate these standard model processes. And so once you fold all of that together, there's not a significant excess of data over the standard model background. So if the number of observed events in black were much greater than the background, that would say, okay, standard model doesn't fully describe what's going on here. There must be invisible Higgs decays. This plot is from a more recent preliminary result that shows another feature that is very interesting. This is the Dijet mass. And so I'll just walk through why this kind of works for vector boson fusion events. You can approximate this as the product of the two PTs times the exponential of the difference in pseudo-rapidity between them, which you can think of as just the average of the jet PT times the exponential of the difference in pseudo-rapidity over 2. So if you have a 100 GeV jet on average, this gets weighted up by about a factor of 10 because there's this exponential term here. So vector boson fusion tends to produce really high Dijet mass events, and it does so more frequently than for the background. So you can see the signal in red, background normalized to a small number, compared to the background processes all stacked on top of each other. And so if you look at the ratio, you see that the sensitivity increases as a function of Dijet mass. I'm not going to go into too much detail here, but there are a few other things that we did improve in addition to just adding data between the last slide and this slide. One of them is that we had some issue making a prediction for the number of events in the past, and so we got around that by improving the way that we generate the Monte Carlo, which we use to get the standard model prediction. And so we made some big improvements there. We also did some improvements in terms of just how many bins in this histogram there are for taking full advantage of the statistics from a whole 4 years of data taking.
We do have a question that came in.
Mm-hmm.
Somebody asked, do various vector boson fusion processes making Higgs, e.g. W plus W produces H and ZZ produces H, always add constructively, or are there situations where interference is destructive? What physics ultimately determines the relative phases of the amplitudes?
Yeah, that's an interesting question. So I think that for vector boson fusion, I think that they are only constructive. I think it's all constructive. I would have to check to be sure, but I think it's only constructive. I think that the biggest contributions from W's would make sense based on the PDFs, but yeah. So I think the biggest contribution is W's, and I don't think there's a destructive term here, but I would have to double check that to be sure.
Thank you.
Mm-hmm. That's an interesting question, though. Right. So this is based on the data that we have. Again, we don't see a substantial deviation of the data compared to the prediction, and so what we do is we use this to make a constraint on the number of on the fraction of invisible decays, and so we usually describe this as a limit, but it tells you what fraction of Higgs decays could decay invisibly and be consistent with your data. So the lower the number, the more sensitive the analysis. And this table shows a couple of numbers. It shows for this vector boson fusion channel, we expect, based on our expectation from the standard model, to allow for 13%, up to 13% of invisible decays to be consistent with the data. Then we do the same calculation, including the data, and it turns out these agree. If there were an additional number of events in the data, this number would be higher, which would tell you that you have attention with the standard model and you've found some new physics. But we haven't, so we can say that just based on this one analysis, only up to 13% of Higgs bosons can decay invisibly. Now, there are other ways you can look for this, and I'm not going to talk about that in a lot of detail, but there's other ways to make a Higgs, and Atlas has looked for a whole bunch of them. And if you include all those together and do a statistical combination, this number reduces by 2%, which is substantial, actually, and gets us to 11%. So we're really probing fairly small branching fractions in terms of the Higgs decays to invisible, and it is much smaller than what you get if we just took the Higgs measurements by themselves. So now I want to set this in a slightly different context and compare it to other kinds of experiments, in particular what we call direct detection. So I focused on the left-hand case here, where you have standard model particles. They interact, for example, through a Higgs indicated dark matter. We make them with a collider. We constrain the branching fraction of Higgs to invisible decays. But there's a whole other class of experiments where the dark matter comes in, it scatters off of a nucleus, and then you look for the evidence of a nuclear recoil. And some of them are listed here, things like Xenon 1ton, Lux, Panda X, Picasso. These are just some examples of direct detection experiments, and they have a very different kind of experimental constraint, which is the upper bound on the cross-section, on the WIMP nucleon cross-section, or the cross-section of this dark matter particle. So we would like to make that comparison, and the way that we do that is by making a simple model. It's probably, you can think of it as a benchmark, and it has a whole bunch of caveats. But essentially what we assume is that on one side we have the standard model, on the other side we have dark matter. The Higgs boson is the only particle that allows these two sectors to talk, so it's the portal between the standard model and the dark sector. And we assume that there's only one species of dark matter, and so given those assumptions, we can make a simple curve to make comparisons to see what the sensitivity is. And so this plot does that. On the y-axis here, we show the nucleon cross-section, WIMP nucleon cross-section, so there's an upper limit, and the x-axis shows the mass. A couple of interesting features. The direct detection experiments, for example, this black dashed line, carve out lines that tend to be more sensitive at higher mass. The reason that the Higgs to invisible lines, depending on the spin, are blue or red, and they lose sensitivity at half the Higgs mass, and that's because above this the decay is off shell, and so there's not sensitivity in this part of the phase space. At lower mass, the direct detection experiments also do have some sensitivity, and these sensitivities are improving as experiments are designed essentially to target this region. And so you can see that there's complementarity with these different regions, and that's a good thing, because ultimately what we want to do is we want to see dark matter in all the different ways that we can think of. And so we'd like to be able to make it in a collider to study it, and also to be able to see it in other experiments as well. So I just want to give a little bit of kind of plan or sketch of other things that you can do using the similar kind of tools. So I've discussed what you can do with Higgs invisible decays using vector boson fusion, but there's a whole bunch of things that leverage very similar techniques. So for example, one thing that is in progress that I can't talk about too much, but I can mention that it exists because theoretically this has been thought of. You can add a photon, which radiates off of the charge W, for example, or off of the initial state radiation from the quark. And turns out this reduces the cross-section substantially, but it also is very clean experimentally. And so we can use similar kinds of techniques for, as I described earlier, but include this photon. And that's a unique way to look for Higgs invisible that we're just kind of probing now. And there's also opportunity for other new physics models as well. You can also have more complicated theories, such as supersymmetry. This can lead to cascade decays, where there's invisible particles from the Higgs and other standard model particles, such as electrons and muons. That's also something that has been discussed and proposed that is in progress now. And then you can do something a little bit different, where instead of making a Higgs and asking if it decays, you can say, well, let's suppose that I produce a supersymmetric particle. I won't go into the details here, but you produce the particle and then it decays to produce a very similar final state, but with some leptons in it. So that has been published already. And so the main message here is that you use similar tools, similar triggers, similar kinds of techniques to address lots of theoretical phase space and open questions. So the last thing I want to talk about in the few minutes of my talk here is about the long-term LHC plans, or the high luminosity LHC. So right now we're roughly 10 years into the LHC program in terms of taking data. We're not taking data currently because we're undergoing an upgrade. But if you kind of zoom out for a minute, you can see this is a much longer program. We have collected about 140 inverse femtobarns of data. It's not quite 150 as shown here, but it's close. And we want to increase that by more than an order of magnitude. So to do that, we have lots of experimental upgrades. We have electronics upgrades that are happening now for the trigger system. And then again, in about 4 years, to upgrade more of the tracking system, and then additional electronics for the trigger again. So there's a lot of work to do for the experiments, and then also for the LHC. So this is the long-term plan. The reason we want to do that, by the way, is because we would like to increase the luminosity, so we have a lot of events recorded. But the only way to do that without running for many, many decades is to increase the number of interactions per crossing. And so you can see on the left right now, we typically end up with something like an average of between 40 and 50 interactions per crossing, which is what this new variable represents. So the events do look relatively complicated, but it's far less complicated than what we'll expect for the high luminosity LHC, where we just have hundreds of interactions in a single event. And so in order to deal with this, we have to make our detector better. So I'm just going to give one example. This comes from a paper that I published this year. It has to deal with the trigger. So this plot shows the rate of the trigger, which is how many events are coming out of the detector for this trigger. And the target is kind of about here, 5 kilohertz, which is roughly 5% of the events that we can save. And so there's a couple of things going on here. One of them is that we are able to do some basic optimization with the same detector and same electronics, but as a function of pileup, this is really dramatically increasing. And so if you manage to extrapolate this from, say, the right-hand side of this plot, which is one of the more extreme runs of run 2 to 200, you would see that this rate would just kind of explode. And so to fix that problem, what you have to do is come up with more solutions. You have to be able to save more data, so you have a higher rate that you can read out from the detector. You need to be able to use more information in the trigger system. So instead of having just a little bit of information from the calorimeter, you need a lot more, and then you need more time to make the decisions in the trigger. So these are some of the kinds of strategies. All of them are being pursued by Atlas for the high luminosity LHC, and they will be necessary to deal with this kind of problem. This one I think is a very interesting example because it directly impacts Higgs invisible and kind of dark matter searches. But the same kind of problem exists for most things you can think to do at the high luminosity LHC. I do want to give just a sense of how things will scale for Higgs invisible in particular. This is not something that came from Atlas, as you can see, but it does show you how things scale. So right now we're sitting roughly around here. We ended up doing, I think, a little bit better than this projection expected. But you can see that as a function of luminosity, depending on the assumptions we make on the analysis, we are probably going to be in the ballpark of a couple percent branching fraction of Higgs invisible sensitivity. But all of these things are really contingent on being able to trigger on the events and the detector upgrades so that we can make sense of very high pileup events. So in order to get this good scaling at the bottom, you need to do these detector upgrades. So in conclusion, I've told you why we should look for invisible Higgs decays. I've told you about the standard model and the problems there. I've told you about the experiments, the Large Hadron Collider. I've told you about the Atlas experiment, so that's the details of how we do it. I gave a lot of details on how we look for Higgs invisible particles, and then told you a little bit about what the long-term plan is. Now, I want to end a little bit by just thinking a little bit more broadly about what it means to discover a new particle. It could be Higgs invisible, it could be something else. But this has a lot of implications. So theoretically, if we discover one new particle, I think the natural question is whether there's a lot of other new particles as well, because the standard model has a significant amount of structure. It has a lot of particles in it, and the dark sector, if you want to think of it that way, it could have a lot of structure as well. And this is not something that's theoretically new. I mentioned supersymmetry several times in the talk, but in this theory, you actually have copies of the standard model with different spins. So the spin half particles become spin one particles, and so on. And so you can see that you have these very different kind of structures theoretically, and you would want to discover all of that. In order to do that, you need a very robust experimental program that is planned many years in advance. So you need to do things like continue the direct detection program experiment. You need to build other accelerators. You might want to build a linear collider that collides electrons and protons to make Higgs bosons and study them very carefully. You might want to build a 100-kilometer accelerator in the far distant future that collides protons at much higher energies to continue to discover maybe higher mass states. So there's really a lot of things that you want to do to fully kind of flesh this out. Of course, the other aspect of this is that this is a very long time scale. So you can see people are actively talking about experiments that will run till the end of the century. And so I just wanted to use this as an opportunity to remind all of ourselves about the importance of public engagement, particularly for young people. One of the things that I found really rewarding this year was that I got involved with a high school. I did some outreach events with them, and I visited their very diverse and enthusiastic class to discuss particle physics several times. In one case, they just had a question and answer period, and then another time we actually visited the Atlas detector virtually. And so you can see some pictures of this visit. I am not in Geneva at the moment, so there was a graduate student who was kind enough to take us through the experiment. But it was really an exciting opportunity to see students starting to engage, and I think it ties in very nicely with the time scale of the kinds of projects that we need to answer these fundamental questions. So, yeah, thank you very much. In summary, what I've discussed is these three sort of eras. The 2010s have been the discovery of the Higgs boson. Now we're trying to probe this as well as we can, and that's something that's going to continue for several more decades. So with the Higgs boson discovered, it's an exciting time to use this as a tool to find new elementary particles and solve fundamental problems in physics.
Well, thank you very much, Dr. Carlson. I greatly appreciate this talk. I'm going to give the audience a second to type in their questions in the Q&A, and while they're doing that, I want to remind everybody that immediately following the talk, we will have a wine and cheese session, a virtual wine and cheese, that is, with our speaker and faculty and students. And faculty and students should already have a link to that meeting room. It's the same that we used earlier during the day for meetings with the speaker. We do have a couple of questions coming in. Someone asked, we have a compound question here. How will you be able to tell whether the missing transverse energy you find is from dark matter and not neutrinos? Also, in the vector boson fusion case, what model are those dark matter particles part of? Does it have a name?
Okay, great. So the first one, let me go back to the plot. Right. This one's probably even a little simpler. So the first question is, how do you know that you've discovered something that is a neutrino, which is in the standard model, versus what you get from something that's not standard model where the Higgs decays invisibly? So basically, we can't tell event by event, which means if you just look at one of those event displays that shows missing transverse momentum, you have no way of knowing if that particular event had a neutrino in it or if it had dark matter. What you can do is this kind of statistical analysis where you say, I'll look at a distribution. It could be this missing ET distribution. And you can say, I can make a prediction for how many events I expect from the standard model process and how many I expect from not the standard model. And so you can statistically look at the sum of all of the events to say whether or not there was something new there. And that's not unique to missing ET. It's actually the same for the Higgs discovery. It's the same for everything that happens at the LHC. You can essentially never look at a single event and say, this event was new physics. You always have to do an analysis over all of the events because there's a lot of background at the LHC, and there are lots of things that look very much like new physics, and the way that you have to do it, to deal with it, is to just take enough data to get to the point where you're convinced that it's not consistent with the standard model background. So it's essentially statistical. The other side of the question is about the vector boson fusion, Higgs, and whether this has a model. So a name. So the easiest way to describe the model is probably the Higgs portal model. Now, that describes actually a little bit broader class of models that has to do with how the Higgs boson decays invisibly. The vector boson fusion part, that's actually a standard model Higgs production. So that applies to the standard model Higgs as well. So you can also make this in other production modes of the Higgs, which I alluded to. And then the decay, usually people will call it the Higgs portal model. I should also say that experimentally, we're making very generic assumptions. We're assuming things like all of the Higgs bosons decay, or we have a model where the Higgs boson just decays invisibly. So it's a fairly model-independent interpretation of the data.
Excellent. We have another question. Does Moore's law help you? Do improved electronics allow for higher rates?
Yes. Well, Moore's law has certainly helped in the past. Where we are now, well, let's see. Let me go back to this slide. There's two parts of the trigger. Moore's law is probably more or less saturated for the software part of the trigger. CPUs are getting they're getting a little bit better, but they're not getting substantially better. So we're really talking about similar-ish technology for the high luminosity LHC. One thing that's different is, you might imagine using custom techniques, like you could imagine using GPUs or something here, and people think about that, but at some level, we're still going to have very similar kinds of technology here. It's going to be better, but it's not going to be dramatically better. FPGAs, I'm not actually sure that this necessarily follows Moore's law. I would need to check that, but FPGAs are getting much, much better. And I can tell you some concrete ways in which the trigger system in the hardware, or the hardware trigger system, is going to get better. In run 1 and run 2, we had roughly 7,000 individual components of the the trigger system, or of the calorimeter coming in. And keep in mind, there are 180,000 ways we can, or readout channels for the calorimeter. So starting now in the upgrade we're doing now, we're going to increase that from 7,000 to 36,000. That's because we have better FPGAs, more advanced electronics. And then going even further to the next upgrade, we're going to be able to do this with every single cell, so 180,000 inputs. So I would need to double check to see whether this is actually following Moore's law. I'm not clear on that, but certainly FPGAs are increasing rapidly, and that is allowing us to deal with the increased data.
Let's do one more question, because we're past the hour here. If dark matter is light, e.g. an axion, does the Higgs sector remain an interesting place to look for signs of it?
Yeah. So if it's really light, my understanding is that the kinds of couplings that would give you this Higgs portal model are probably not theoretically well motivated. I think that there's a term for this. I can't remember it off the top of my head, but it's well motivated down to about a GeV. Below that, I think this kind of Higgs portal model where the Higgs decays to invisible particles below about a GeV. This is not something that's theoretically expected. It is, on the other hand, experimentally, when we do the search, the mass of the state doesn't matter at all. We could have essentially massless or very low mass invisible particles, and the way we do the search is completely sensitive to those.
Okay, well, at this point, we're out of time, but I'm going to invite people with more questions to please join us in the wine and cheese session. And I want to thank our speaker one more time for this excellent talk today, and thank our audience for joining us. And thank you all very much.
Thank you.